So we're still trying to figure out really what the crux of optical behavior is. And at this point, we know enough. We've asked enough questions to kind of lead us to believe that this model we've used a little bit, which has helped us out, where the atom as a sphere is insufficient. So it was useful for some mechanical analogies, for some other purposes. Even if you extend that out to a string of spheres, as you do for a polymer, I often just draw it as a squiggly line or something. It still didn't really explain the interaction um, with light, or in fact, really with any electromagnetic radiation. So we need to get inside. We need to crack this thing open. We need to get inside the sphere. Right, so let's do that. And I think that we can proceed fairly quickly, um, assuming a certain level of background knowledge. So inside the atom, we've got a nucleus, and the nucleus contains protons, which are positively charged, and neutrons, which are neutral in charge, as the name implies, right? Neutral charge. But this is most of the mass of the atom, essentially all of it. I mean, 1,000 times or so lighter than that is the electron. So most of the mass of the atom comes from the nucleus, and then orbiting around the nucleus are electrons. And the electrons have a negative charge. And in fact, that's that charge that I'm referring to here, this positive charge, negative charge, these are the same quantity but opposite signs. And those are equal to 1.602 times 10 to the minus 19 coulombs. That's the fundamental charge. Fundamental charge. And the nucleus, particularly, in fact, the number of protons, is what determines the element. It's like the social insurance number for the element. So sometimes we even refer to the proton number, or the atomic number. Okay, I actually kind of like the name proton number. Depending on where you are exactly, atomic number is probably a little bit more commonly used, but they're generally understood by I think most people as referring to the same thing. And we use the letter Z, uppercase letter Z, to denote the atomic number. So that determines the element. For example, carbon has an atomic number of 6, and that's carbon. You can also have a differing number of neutrons, and that can create, what that does, that creates what we call isotopes. Differing number of neutrons, so they'll have a different mass, but they've got the same number of protons, same proton number, but they have a different mass. And so a differing number of neutrons creates different isotopes. So an example of that would be carbon 13. Okay, well, it's carbon, so it's got to have 6 protons. Otherwise, it's not carbon. But if it's got a mass of 13, these mass units. In fact, sometimes they're called atomic mass units, and it's going to have 7 neutrons. And the first look at the atom that we're going to do, which is somewhat useful, has a central nucleus. With electrons in specific shells. Oh my goodness. Let me try that one more time. Specific shell. I'm trying to get these things to be kind of concentric. These shells surrounding the nucleus. And you could have an electron in one of those shells, electron in shell. Okay, and the model that we're looking at now is really, if this was just hydrogen, this is called the Bohr model. Here we go. I'm gonna make this okay. The Bohr model, after Niels Bohr, and it has the central nucleus with electrons orbiting in shells. And one of the features of this model is that the distance of the electron from the nucleus is limited to specific values. So n equals 1, n equals 2. I erased a space and then I realized I didn't make it big enough to fit my writing in. N equals 3. So these are these different shells, different distances, but they are defined. This is an important feature. Defined distance from the nucleus. Distance from nucleus. Okay, and so this model is, it's not entirely correct. There's limitations to it. There's problems with it. But again, it's a model, and so we'll see it's actually useful for certain discussions. In fact, one thing that's actually quite useful for discussing is, what if you could cause an electron to move from this shell here closest to the nucleus to a shell at a further distance? Or in fact, you could raise the question of, well, what if I wanted to move here, halfway between n equals 2 and n equals 3? Well, the Bohr model tells us, because these are defined distances, that you can't do that. You can't move part way. And in fact, it tells us that you have to put some energy in to the system to cause an electron to be excited. So that would be so-called excited electron. And that was energy in. How could you put energy in? Well, you could put energy in the form of electromagnetic radiation. E equals hc over lambda. So you could put some radiation in, excite an electron, and the other thing that you could do is, if you had an atom where you had excited an electron, and what I'm going to do is I'm going to leave a little kind of hole there to show, actually I'm going to take that away, it might be confusing. So here's the electron, and this is the excited. It's having so much fun. It's excited. Sorry. It's the excited electron. It's been increased in energy level. It's in this temporary high energy at n equals 2, and it's only temporary. It's gonna want to drop down to achieve a lower energy. And so what happens is it drops back down, and it's only this specific value, right? We say these defined distances. What that tells us is that, another way of saying that is that the energy is quantized. Quantized. Quantized means that it can only take on specific values. Letter grades, A, B, C, D, are quantized, whereas percentage is more continuous. So if this excited electron drops back down, it gives off energy. Okay? And because it's quantized, it's a little packet of energy, if you will. It's a packet. It's like a specific quantity of energy. We call that a photon. So the Bohr model is useful for discussing certain things, particularly transitions in energy levels to either give off if an electron drops down to lower energy, or if energy goes in to excite an electron. The Bohr model is useful for describing those, but it also has its limitations, which we'll get to shortly. Proceed fairly quickly, assuming a certain level of background knowledge. So inside the atom, we've got a nucleus, and the nucleus contains protons. So we're still trying to figure out really what the crux of optical behavior is, and at this point we know enough. We've asked enough questions to kind of. So we need to get inside. We need to crack this thing open. We need to get inside the sphere. Right. So let's do that. And I think that we can put a string of spheres, as you do for a polymer. I often just draw it as a squiggly line or something. It still didn't really explain the interaction with light, or in fact, really with any electromagnetic radiation. Lead us to believe that this model we've used a little bit, this has helped us out, where the atom as a sphere is insufficient. So it was useful for some mechanical analogies, for some other purposes. Even if you extend that out to a